It arcs, explodes, and blisters steel. It's used to make 50% of all products, and it puts the power to build a skyscraper in a man's hands. By friction or robot, even underwater. These are the tools that the world can't live without. Now, welding on Modern Marvels. Las Vegas, Nevada. Perhaps nowhere else in the world does the old come down as spectacularly. And the new rise up as quickly.
Right now you're in the east wing of the new Palazzo Hotel. We're on the 38th floor. There we go, laying deck.
The Palazzo Hotel will be the central hub of the world's largest resort, hotel, and casino complex. And without the power of welding, it couldn't be built. Armed with high-power welding guns, and with nothing more than a safety harness between them and the ground below, these iron workers will weld a quantity of steel nearly equal to the amount in the Brooklyn Bridge, Statue of Liberty, and Empire State Building combined.
There's just shy of 70,000 tons of structural steel.
Adrenaline runs high for welders working at such heights. And with so much electricity in use, the dangers are real.
This particular machine runs on 480 three-phase. It's fed with 200 amps. At 480, if you make a mistake, you're not here tomorrow. It's almost instantaneous death.
By definition, welding joins two separate pieces of material through high energy. No other joining method forms a more direct and powerful bond.
All the other methods, whether it's rivets, whether it's bolts, even if it's glues and adhesives, you wind up putting in extra material in order to make the connection. In the case of welding connections, bring the two pieces together, put a weld in between. It's a very efficient way of joining material.
But efficiency is only half the story, because welding creates a bond along a seam or joint that is nearly always stronger than the base metals used to form it.
The tensile strength of the welded material itself is actually greater than the material you're welding. A good weld, the material itself will tear before the weld will tear.
The source of this strength is more than just surface deep, and goes right down to the steel's very atoms. Every atom within a beam possesses electrons that encircle it in what is called an electron cloud. When a welder applies intense heat, the atoms are slammed together so forcefully that they begin to share a single united electron cloud. Now locked as one, these new molecules are more powerful together than separate. For many centuries, the only way to make these welded bonds was with furnace and hammer, a process now known as forge welding.
With forge welding, two pieces of material are put lapped over each other, heated, not to the point of melting, but until they're hot, and then hammered together. That hammering together of the two metals will achieve the same metallic bonds that today we'd form with an electric arc.
Today, electricity has replaced the brute force of the forger's hammer to construct our world. From the car you drive, to the plane you fly, and everywhere in between. The most common method is known as electric arc welding, which is based on principles first discovered at the turn of the 19th century. Those principles revealed that electric current will jump the gap between two nearby metal conductors to form a completed electrical circuit. This jump, known as an electric arc, generates a spark-like discharge that is both extremely bright and intensely hot.
The arc is estimated to be between 6,000 and 8,000 degrees Fahrenheit. That's the same temperature as the sun. Steel melts in and around 3,000 degrees, so this 6,000 to 8,000 degree arc is more than ample heat to melt the steel that we're joining.
By the 1890s, engineers had harnessed this intense newfound energy to create the first electric arc welds. A work lead, or ground, was attached to one corner of the metal to be welded. Electric current then flowed from a generator through a long conductive metal stick, known as an electrode. As the stick neared the grounded metal, an electric arc was formed, causing heat to melt the metal. The apparatus was crude, but the basics were sound, and are now reflected in the simplest arc welding form in use today, stick welding.
The basics of the process are, you have an electrode holder, you have a cable that runs back to the machine to pick up the welding current, and you place the bare end of the electrode in the holder, and it picks up electrical contact there, conducts current down to the end of the electrode, which is bare. The technique is touching the electrode against the work and then moving it far enough away to establish an arc, but not so far it goes out. And if you leave it too close, it'll stick. You pull it away too far, it'll go out. So the trick is to get your bounce where it's just about right.
When the arc is struck and positioned near the metal pieces, the intense heat causes both the electrode and the metal along the seam to melt together into what is called the puddle. Until it hardens, this molten puddle must be protected, even from the very air that we breathe.
The air we breathe is about 80% nitrogen and about 19% oxygen. It's really good for breathing, but it's not good for liquid metal. And just like we dissolve sugar in hot coffee, these gases dissolve in liquid metal. When the metal solidifies, the gas percolates out, and that makes holes in the welds.
The dangerous result could be a weak, even brittle weld. So to shield the puddle, a chemical coating is applied to the electrode. As it melts under the heat of the arc, this chemical coating dissolves into shielding gases that envelop and protect the weld, keeping it free of air. This is known as shielded metal arc welding. And as the technology evolved, the coating took on even greater significance.
The chemical coating has three functions. Some of the coating forms shielding gases at the heat of the arc that protect the weld from the atmosphere. Some of the chemicals at the heat of that arc form a liquid, slag, which protects the welds as the shielding gases move along. And some of the elements are alloyed into the deposit to make it a high-strength deposit. So three things happen while you're moving this arc along the work.
When the weld is complete and is cooled, the slag is chipped away to reveal the trail of welded metal, known as the bead. Getting the proper length, depth, and form of the puddle along the bead takes years of practice.
There's so many variables when you weld. There's very few times that two things you weld together are the same. Either the metal changes, the thickness of metal, the environment you're in, the conditions the metal is used for. There's just so many things change that you have to know a lot of different things about welding.
Complicating matters are the safety requirements, beginning with the welder's mask. Just as staring into the sun can damage your eyes, so too can an electric arc. Therefore, protection is crucial.
When you first flip it down, it's dark. You can't see anything, but you quickly get comfortable with it. Once you strike the arc, it's like a big flashlight. You can see what you're doing.
Although electric arc welding was first discovered in the 1800s, its acceptance was slow in coming.
Anything new, they fight. It wasn't thoroughly accepted, so it took time to make the transition into the welding process.
No company was more influential in changing the tide than Lincoln Electric Company of Cleveland, Ohio. Today, Lincoln Electric is the largest manufacturer of welding equipment and consumables in the world. That success is rooted in Lincoln's commitment to proving the viability of welding, even in the face of constant doubters. And no industry was initially more skeptical than the biggest one of all, building construction, where rivets were king, well into the 1940s.
Rivets were intuitive. If you think about it, putting in something with a head on either side, that makes sense. Welding had some mystery about it.
But riveting was also extremely difficult work. It required fabricators to hole punch the steel beams. Then a team of workers aligned those holes to their exact counterpart. Rivets were heated in a central oven, then hurled to the proper joint.
He would heat the rivets, and once they got heated, he would throw them to the person who was actually standing at the point waiting for the first rivet. So you had a pitcher, a catcher, with a set of tongs who would slide it into the hole, and then you had a guy bucket, and then you had a riveter, and the riveter would round the head on the opposite side.
Significantly, rivets limited the design options for architects and building engineers.
A lot of very famous and beautiful work is done with rivets. But basically, you're building a box with a design to the inside of the box. You can only carry so much shear on that connection.
In 1928, Lincoln Electric joined with a local architectural firm to erect the first commercial building wholly constructed from arc-welded steel. In the Upper Carnegie Building, the typical dense network of riveted steel was replaced by a series of continuously welded beams that ran the entire length and height of the building. Not only did welding free up space, but these continuous beams carried even greater loads and stresses than their riveted counterparts.
Connections are always the weak point in a structure. Connecting things together is always a challenge. But welding changed all that. Literally, if you could get the material in the configuration you wanted it, there was a way to weld it together.
Today, skyscrapers come in many shapes and sizes, in large part because continuous beams can be fabricated and welded into curves and unique angles. To construct these beams, welders will make 30 to 40 passes on the crucial joints, using Lincoln Electric's latest flux core welding technology. Here, the traditional stick electrode has been replaced by wire on a roll that feeds directly into the welder's gun. The chemical flux that protects the weld from the air is now contained within the wire itself and melts just as before.
There's approximately 90 tons of weld wire will be used and consumed in this project alone. That's somewhere around 180 million inches or 2,800 miles of weld wire. You could stretch a single wire from LA to New York and have leftover.
On the largest beams, which can weigh as much as 900 pounds per linear foot, a team of welders can work on a single weld for hours.
The columns that we're looking at right now are basically supporting the entire east wing of this tower. Originally, these pieces were so long, the capacity of the cranes would not pick them up and set them. So we had to cut them down, make them lighter, so the crane could set them. And the engineers wouldn't allow us to make that a bolted splice. It had to become a welded splice. It's about a 30-hour weld. I believe we had 2 guys working on that simultaneously for 30 hours of welding.
Welding really enabled the architect, the engineer, to dream bigger dreams, make bigger bridges, make taller skyscrapers, and to do so in a reliable and dependable way.
But at the end of the day, those big dreams are only as solid as the ironworkers who weld them together.
We're not presidents. We don't get monuments built to us. But when you look across the skyline, ironworkers have changed the way that looks.
But electric arcs aren't the only way to make a weld. In fact, others are a real blast. Pennsylvania's Allegheny Mountains, birthplace of American steel. Here in the hillsides that surround historic mill towns, the most powerful welding process of all occurs, more than half a mile underground.
Fire in the hole!
It's called explosion welding. And with a force measured in millions of pounds per square inch, explosion welding does what no other welding method can. Join nearly every kind of metal together, no matter the type or composition.
Explosion welding allows highly dissimilar metals such as aluminum, carbon steel, alloy steel, stainless steels, alloys of copper, all can be welded to one another.
The result? A single welded piece known as clad that combines the best characteristics of each metal involved. Wherever there is high heat, intense pressure, or corrosive liquids and gases, clad is probably there.
Could be a column, it could be a heat exchanger, it could be a horizontal tank. But when you see a chemical complex or an oil refinery, there'll be a lot of clad metal in there.
To create an explosion weld, two large pieces of metal are stacked atop one another, then covered with a high-powered explosive. When detonated, the downward force of the explosion welds the two pieces together through a combination of intense force and remarkable physics.
What you can see here, and it's very clear, you have two different materials. Stainless steel is a darker gray, a lighter gray for the carbon steel material. The detonation was initiated at this point, and you can see the deformation from our initiator. That starts the explosion, and the explosion rolls across the entire top surface of the plate, zipping the two together.
No one would have ever thought such a violent process could be controlled and mastered had it not been for the devastation and havoc of World War I, and later, World War II.
The origin of explosion welding was first observed during the First World War, when shrapnel may have stuck to armament. It wasn't just stuck, but it was actually welded.
There was only one possible explanation: the explosive force these metal pieces had endured.
It was an observed phenomenon that was later duplicated in the laboratories and practiced commercially.
Today, Dynamics Materials Corporation is a world leader in explosion welding technology. Here, the decades-old discoveries from the battlefield have been refined into an exacting science. The explosion welding process begins as soon as the two metal plates arrive at DMC's main plant, outside of Pittsburgh, Pennsylvania. To maximize the welding force of the explosion, the surfaces of each plate are ground as uniformly flat as possible, a process that also removes any rust, oxides, and other surface flaws. They're then ready to be assembled into the pack, which locks the plates into position for the explosion. To build a pack, the stronger and thicker of the two plates is laid face up. From now on, this plate will be identified as the backer. Small metal spacers of equal height are then tacked onto the surface of the backer in a uniform grid. These spacers will maintain a set gap between the backer and the second plate, which is placed on top. This second plate is thinner than the backer and is called the cladder. The standoff gap between the backer and cladder is less than an inch in height. Yet without it, the explosion weld would be impossible. In the final stage of assembling the pack,